Today, friends, we were going through the design of canal sections, in which in the previous video we have designed the non-alluvial canals. Now in this video we'll be designing the alluvial canal. So stay tuned to this channel for the complete informations on the design of alluvial canal. So before proceeding to this lecture, at first I want to say that failures inspire winners and defeat losers. So this is the inspirational and motivational quote that I have taken from the book called Rich Dad and Poor Dad. Okay. So if you are new to this channel, you can like, share and subscribe this channel as well. So let us move into the video now. So design of alluvial canal. The soil which is formed by the transportation and deposition of the silt through the agency of water over the course of time is the alluvial soil, and the channel that is constructed across or constructed within or constructed over the alluvial soil is the alluvial canal. So alluvial canal are those that are excavated through the alluvial soils such as silt, and they carry a lot of silt along with water. So these are those channels in which the water is carrying a lot of silts, and if you construct such a channel, so that is known as the alluvial canal. So there are different theories for the design of alluvial channel. So for the design of alluvial channel, first theory is the Kennedy theory. Likewise, the second theory is the Lacey's theory, and third is the tractive force theory. So first we'll be dealing with the Kennedy's theory. Okay. So for the design of alluvial channel, Kennedy theory states that the silt carried by water flowing in a channel is kept in suspension solely by the vertical components of edges, which are generated over the full width of channel and rise up gently to the surface. So by plotting the observation of the mean velocity and depth of flow, Kennedy obtained a relation between the critical velocity and depth of flow. So the critical velocity V naught can be given by the formula V naught equals to 0.55 d to the power 0.64, where V naught is the critical velocity with same silt grade as that of Kennedy's channel. So Kennedy performed his experiment in the silt grade of Upper Bari Doab Canal that is located in Pakistan. So this is the channel in which Kennedy performed his theoretical and experimental procedures. So in that canal, the silt grade is taken as that of standard one, isn't it? So that is the standard silt grade that is used in the design of, in the theory making of Kennedy's. So V naught is the critical velocity with same silt grade as that of Kennedy channel. So if we may have another silt grade as well, because it is not always necessary that we are having the same silt grade as that is located in Upper Bari Canal. So for other silt grade, there comes another term known as critical velocity ratio. So for accounting the silt grade, we have the formula V equals to 0.55 m d, 0 d to the power 0.64, where V is the critical velocity of channel with any kind of the silt, D is the depth of the flow, M is the critical velocity ratio, CVR, that is given by V by V naught. So whenever you have determined the critical velocity of channel with any kind of the silt, that is V, and if you divide it by the critical velocity with same silt grade as that of the Kennedy's channel, so then we have this critical velocity ratio. And for the determination of the mean velocity of flow in the channel, Kennedy used the Cotter's equation. So as stated earlier, the Cotter's equation, we have the velocity, that is mean velocity of flow is given by V equals to C root RS. So here C is the constant, Cotter's constant, and it is given as by formula as shown in the board, that is C equals to 1 by N plus 23 plus 0.00155 by S plus divided by 1 plus 23 plus 0.00155 by S 0.00155 by S and root R. So V is given as V equals to C root RS. The flow equations that are used in the Kennedy's theory are that you need to equate discharge equals to area into velocity, and this critical velocity through the canal having specific field grade M, ratio M, as V naught equals to 0.55 M d d to the power 0.64, and the velocity, the mean velocity is given by the Cotter's equations. Now in the Kennedy's theory design procedures, we have the two design cases. So in case one is that when your discharge, the rugosity constant, the critical velocity ratio M, and the bandwidth to depth ratio is given, then you need to design the canal by Kennedy's theory. So for that, you need to calculate the cross-sectional area in terms of D first. So using, if you are taking that it is a trapezoidal section, then you can simply apply area cross section equals to BD plus ZD square. So this may be the equation first. Then substitute the value of area from first, and velocity V naught equals to 0.55 MD 0.64 in Q equals to AB to find D. So in step second, you need to do is that in equation first you have obtained the area. Okay, so this area and the velocity can be obtained from V equals to 0.55 M D D to the power 0.64. So this critical velocity V and this discharge, this area is obtained. So you can just apply the continuity equation Q equals to AB to find out the D. Okay, so D is the depth of the canal. So after determining D, you need to calculate the bed width B and the hydraulic radius R. So after determining the D, we need to determine the critical velocity ratio. So this critical velocity ratio, actual critical velocity ratio B naught, from formula B naught equals to 0.55 MD to the power 0.64. So if after determining all this, that is velocity, critical velocity, this hydraulic radius, and so we can determine the bed slope of the canal using the Cotter's equation as V equals to C root RSO, where C is the Cotter's constant, can be obtained from the above expression. So from the above design procedures, we have a one problem that design a canal by Kennedy's theory using discharge. Q is given as 40 Qmac, 40 cubic meter per second. The ratio of base width to depth is 8. The value of Cotter's coefficient N equals to 0.0225, and the critical velocity ratio CBR, that is M equals to 1. So V by V naught value has been given as 1, and you need to design the canal using the Kennedy's theory where Q, N, M and B by D ratio is been given. Now the solution of this problem is that given, we are given that discharge is 40 cubic, B by D ratio has been given, the Cotter's coefficient is also be given, and the CBR is also given, that is critical velocity ratio M is given. So we need to just substitute everything in terms of D, and if you solve everything, so the expression in terms of D, we will be able to solve the expression and get the value of D. So as stated in previous procedures, at first we need to determine the area of the cross section. So assuming the trapezoidal channel, in this case we have the area of cross section, area A equals to BD plus ZD squared. So area A equals to B is your A times D, isn't it? So as it is given from B by D ratio, B is the A times D plus 0.5 D square. So area can be written as 8.5 D square. So here we assume that the Z, that is the slope, we assume that 0.5 horizontal used to 1 vertical. So it's cut, we assume it, the channel being cutting. So the side slope of the channel is assumed as 0.5 horizontal used to 1 vertical. So you can assume between 0.5 horizontal to 1 vertical to 1 used to 1 or 1.5 used to 1. So this is the ranging value of the side slope. So area on the basis of different soil parameters, you need to have that side slope. So area can be determined as 8.5 D square. So second step is to find the velocity using the critical velocity formula. The critical velocity V naught equals to 0.55 m d 0.64. So if you solve this, putting m equals to 1, then you will obtain V naught equals to 0.55 d to the power 0.64. So this is the expression 2. Now friends, we need to use the continuity equations. We have determined the cross-sectional area and the critical the velocity ratio V naught. So all we need to do is to apply the continuity equations and substitute the values, and we can easily obtain the depth of the canal as 2.25 meters. So if you substitute this value of D in B by D equals to 8, then you can easily obtain the value of the bed width of the canal as 18.04 meters. Likewise, friend, we need to determine the hydraulic radius R. So hydraulic radius R can be given by the formula of the ratio of weighted area to weighted parameter. So weighted cross-sectional area and cross-sectional parameter. So area is 8.5 D squared. If you substitute the value of D as obtained previously, and P is the parameter of the trapezoidal section, that is B plus 2D times 1 plus Z squared, square root of 1 plus Z squared. So if you solve this, you will receive the hydraulic radius as 1.87 meters. Now friends, we will determine the value of the critical velocity ratio V naught. So V naught can be given by the formula V naught equals to 0.55 m d 0.64 d to the power 0.64. So if you solve this, you will obtain the critical velocity ratio V naught as 0.92 meter per second. So friends, the last step is to determine the side slope S. So friends, the last step is to determine the bed slope S. So the bed slope can be determined from the Cotter's formula, that V naught equals to 1 by n 1 plus 23 plus 0.00155 by s divided by 1 plus bracket 23 plus 0.0015 by s and root r multiplied by root RSO. So this is the formula of Cotter's equations. So in which we have already determined the critical velocity ratio V naught. We have determined the hydraulic radius R. Likewise, we have determined all the necessary parameters, like we have given the Cotter's coefficient we have given. So the only unknown is the bed slope. So unknown is the bed slope of the canal. So solving this and substituting the values, we will obtain the bed slope as 1 in 5405 meters. So this is the one you have to go 1 meter vertical in 5405 meters horizontal. So this is the bed slope of the canal that is to be provided. So 1 in 5405 is the bed slope. So friends, at last we need to provide the trapezoidal channel section of side slope 0.5 used to 1, having depth is 2.25 meters, the bed width is 18.04 meters, and the slope of the bed S is 1 in 5405 meters. So this is the design aspect of case 1, in which we are given Q B by D ratio and the critical velocity ratio. Now friends, the second case of Kennedy's theory design procedures of alluvial channel is that you have the known values as discharge, the Cotter's coefficient, the critical velocity ratio, and the bed slope. So these are the known parameters, and you need to design the canal using this Kennedy's theory. So for this, we need to, in step 1, we need to assume a trial value of depth D. So we need to assume an arbitrary trial value of depth D. So the depth of the canal is assumed first. Okay, at first we need to assume the depth of the channel. So after assuming a trial value, we need to calculate the critical velocity ratio V naught. So you can use V naught equals to 0.55 md to the power 0.64. So you can find out the critical velocity ratio, critical velocity from this expression. Okay, so again you can also determine the cross-sectional area using the continuity equation. So you are known that discharge is given and you have just recently obtained the critical velocity. So you can simply calculate the cross-sectional area A. Okay, so after that you need to determine the bed width. So you need to assume in step 4 you need to determine the bed width assuming a suitable side slope. So you have obtained the cross-sectional area A, so you can just assume a trapezoidal section and put A equals to BD plus ZD square. So and you can assume a suitable side slope in the trapezoidal section. Suppose if not given, you can assume 0.5 horizontal used to 1 vertical. Okay, you can calculate the parameters of that is the bed width. Likewise, you can determine the weighted parameter. The weighted parameter P can be given through the formula P equals to B plus 2D 1 plus Z square in case of trapezoidal channel. After calculating area parameter, you can simply determine the hydraulic mean radius R in step 6. You can determine the hydraulic mean radius R using R equals to A by P. Okay. At last, you need to compute the mean velocity using the Cotter's equation. So you know that the Cotter's equations. So using that expression, you can determine the mean velocity. So you have obtained one velocity, that is critical velocity, from the theory Kennedy's expression, that is V naught equals to 0.55 md to the power 0.64. Again, you have obtained the mean velocity using the Cotter's equation. So you need to check the value obtained in step 2 and step 7. So step 2 and step 7th values are compared. Okay, so if they are same, then the assumed depth is correct. So if the values are different, they do not match with each other. Whenever they do not match with each other, then you need to assume another trial value of the depth of the channel or canal and check the values that are obtained in the step 2 and step 7th. So until and unless you find that these values are approaching or converging near or equals to each other, so you cannot assess the correct depth of the channel. So for assessing the correct depth of the channel, all you have to assess that these two value obtained in the step second and the step seventh are matched, and consequently you can solve the problem.
So friends, if you find this video as useful, you can like and share to your friends. And for such videos, stay tuned to this channel. Thank you. We will meet soon in another video.